So welcome back. Good morning, everyone. I welcome you all to the next technical session of the Faculty Development Program on the Deep Learning for Computer Vision. And now I would like to welcome Dr. Vipul Kumar Mishra, Professor, Department of Computer Science and Engineering, Bennett University, for the next technical session on image segmentation using UNet. Dr. Vipul Kumar Mishra is working as an Assistant Professor, Department of Computer Science and Engineering, Bennett University. Dr. Vipul Kumar Mishra is a postdoc scholar from University of Kentucky, USA, Doctor of Philosophy, PhD, Computer Science and Engineering from Indian Institute of Technology, Indore, ME and BE in Computer Science and Engineering. His research areas include high-level synthesis, reversible logic synthesis, emerging technologies, optimization in VLSI design, and swarm optimization. Welcome, sir. Now over to you, sir, for the technical session.
So thank you, Madhu, for giving this nice introduction. So first of all, do I need to switch on my video for entire session or like in the initial section only?
So just for some few minutes only. You
Okay,
can
that's
switch
fine.
off your video after that.
Fine, fine. Because anyways, I'm not able to see my video. Sometimes my hand will come in between, so that doesn't make some sense. Uh, okay, so welcome you all in this FDP workshop. And as Madhu said, today I'm going to talk about the segmentation. So this is a hands-on session, means we'll do entire lab where we will perform some segmentation task with the help of UNet. But before jumping into the lab, I thought let's give some brief introduction of segmentation itself so that you'll have some information related to the segmentation and how it is different from other tasks in image processing such as classification, object detection, and what are different other techniques as well. So that you will have a brief background of segmentation and then we will do the lab session. So let me quickly share my presentation. So is my screen is visible? Please
Yes,
confirm.
sir. Yes, sir. Your screen is visible.
Great. So quickly, here we have to understand first what is segmentation and how it is different from other tasks in the image processing. So in general, if you look into the computer vision side, so these are few well-known or well-defined tasks. One is the classification. Second is the classification with localization, object detection, and instance segmentation. Right. So you can say when we talk about the classification, so you will have a single picture and from that picture you have to classify in one of the class. Right. So then it's a classification task. Now the challenge will start, suppose instead of only one single cat, I have cat as well, dog as well, and some other things as well. Then might be this classification result. You can say, okay, I can see dog as well, I can see cat as well. So how you can classify with cat or dog? So in that case, it will be more challenging. But still, classification is valid in many domains or many particular applications, such as in the medical, where you have to just tell a answer like after looking the image that a particular person is have disease or not, or he is a healthy patient, right? So or healthy person instead of saying healthy patient, because if it is patient, then he cannot be healthy, or he or she. So it should be healthy person. So in that case, similarly, suppose you have single task or single, you can say object, and you just make sure where is that object, the location of that object, and you are putting a bounding box on the top of it. Then it's known as the localization. Again, localization in real scenario, it may be not fruitful or not useful. So then when we have multiple objects, and then we have to make a bounding boxes, right? We have make multiple bounding boxes in multiple objects, means that will give you two information. In case of object detection, this will give you two information. First information, in which class this box is belonging. So you can say class information. Along with that, the location. Location means you have a box on the top of it, right? So this will give you information where is that particular object and who is that object, the classification. Now again, if you look into this bounding box, and suppose I'm dealing with some medical domain, or I'm dealing with some agriculture site, and we have to identify how much area is belonging to particular crop. Or if you are talking about the medical domain, you can say how much infected area in that particular, you can say in particular slide. So now in that case, if you use this bounding box, then there is one problem. Here is a lot of space, lot of things, or you can say a lot of area that not belonging to that class, but still because of this square reason, or you can say rectangular reason, that is belonging to this particular class. So you can see what I highlighted here. Now, in case of medical domain, suppose I'm saying how much it is infected. So you have to give a number. Okay, this is the infection, and that number is coming from the area covered by that particular disease. So now if you use object detection, then it's a challenge, or you can say you will not get most appropriate information. So in order to get that most appropriate, I want to rid of this extra reason as well from this detection. And then this particular concept is known as the segmentation, where we are segmenting individual objects just only belonging to that object. Now you can say, okay, now it's really nice, like you are not taking any additional reason. There is no additional reason that is covered by this dog. So means whatever reason we are saying, that is only belong to that dog. And that is heavily useful while we are talking about the building instruction from the satellite images, or you can say particular disease infected point from the slide, or you can say you have to find out the crop in a particular region from the satellite image, and many other applications are there. So that's thing is giving you a motivation. Yes, segmentation is really required. So now when we understand, okay, the segmentation is really required in many domain. So what different type of thing can be there? How we can solve this challenge? So one thing is the semantic segmentation. What semantic segmentation is talk about? Let's look into this image, right? Now in this image, if I will say, just look at this pixel and just tell me, is this pixel is belonging to tree, or it is belonging to person, or it is belonging to car, right? Right. Suppose you have these three classes available, right? Or it is belonging to some building. So then immediately you will look into this pixel and you will say it is belonging to tree. Right. Next, suppose I am putting a point here. So then immediately you can say this pixel belong to a person. Now once you put some pixel here, now you will say this pixel belong to the car. So ultimately, if you want this kind of output, then you have to go with the pixel wise classification. So you can say segmentation is nothing but it's a pixel wise classification. Right, where we are picking each pixel and then we will say it is belong to which class. Right, so now you can say once you do this exercise in this entire image, you will go one pixel at a time and move from each pixels, you will get this kind of classification. So whatever belong to tree, it will give a one color, whatever belong to car, it will give a different color, whatever belong to the person, it will give different color, maybe cycle, different color. So this is known as semantic segmentation. Right. So I hope you are able to understand the difference between object detection and semantic segmentation. Now, where it can be utilized or what are different applications? So you can say in the autonomous driving, this is heavily useful. Industrial inspection. Suppose you are in some steel plant, or suppose you are somewhere in the in particular manufacturing plant. Now, if you say I'm in the manufacturing plant and I have to find out that particular slide, suppose I have this slide, entire slide available, you can say this is the sheet of steel. Now I have to find out the defect in the steel. So if suppose your defect is something like this, and suppose you are using the object detection, maybe you can put a box. So then defect size will be higher. So in the industrial inspection, they are looking for the semantic segmentation, right? Similarly, we have to look into the satellite images. What are the different regions that is belong to the water? What are the different regions that is belong to the green area? What are the different regions that is belong to the build up area? So these all things we are looking for the segmentation or semantic segmentation. Similarly, as I discussed, like medical imaging, it is heavily used in the medical imaging, right? So now when we say it's a semantic segmentation, so we understand what is the problem, right? The problem that we define, that is the pixel wise classification. Once we say pixel wise classification, then their evaluation is also, whenever we evaluate it, that should also be a pixel wise concept. So here you can say the evaluation of this particular segmentation will go with the pixel wise. How many pixels are correctly predicted, divide by total number of pixels. That will give you the accuracy. Similarly, on the top of it, instead of accuracy, suppose you are looking for another matrix, that is the overlap area. So that is the Jacquard matrix or intersection over union. So you can look it from this image. So this will say area of overlap. So you can say one part, maybe this is belong to your prediction, right? And this one is belong to your ground truth, right? So you will say how much area of prediction is overlapping with the ground truth. Divide by total area. This will give you another matrix, that is IOU, that will help you to evaluate your performance of algorithm, right? It is a good or bad, whatever. Now, there are many ways to do this segmentation. So one very simple way is the fully convolution neural network. So what exactly we are doing in this fully convolution neural network? So let me give you a brief of this with the help of diagram. Then maybe you'll understand much better. So what we are doing, one important point, if you look into the input image and output image, right? Now in this input image and output image, there is one thing is common, the size. If this is your image is your 512 cross 512, then output will also be 512 cross 512, the same size. The only difference in this pixel information. So now you can say here we have given this image as an input. Now it will take a convolution layer, then another convolution layer, then another convolution layer, and finally you will take a argument max and you will classify each pixel. Every pixel belong to each class. And once you club them, those classification, then you can say it will give you the output of segmented image. So maybe inside it, you can say this will look like this is your zero class. So this all will give the zero answer here, right? Similarly, maybe it will belong to one class. So it will give 1, 1, 1, 1, 1, all these pixels. Maybe it is 2, 2, 2, the blue areas, the water area. Similarly, this pathway can be your third class. So every pixel of this will give the answer 3. Similarly, this person will belong to fourth class. So every pixel will give the output of 4. So in that way, your you can say output will be generated. Every pixel have some classification information that is belong to which class, right? So I hope you got an idea like how fully connected network is working. Now question is why this fully convolution neural network is required. So one thing is possible. You can take this one pixel and make a classification and tell you the answer, what is the output of that. And maybe that can be, you can say short network or a small network. But in fully connected network, this is also operate in parallel. This will operate in parallel. So you can give the entire image and this network will take this image in the pixel wise and produce the output in one go. So instead of going sequential, you can go parallelly and produce the entire output in one go. So that's why we require fully convolution neural network. Here we do not have any, you can say fully connected layer, right? We do not have fully connected layer. Right? Now you can say why fully connected layer is not there. So if you are able to recall VGG16 or LXNet, there is in the end there is one network that is fully connected network is there, or fully connected layer is there. Now the information of this layer will come based on the output of the previous layer, or you can say the information from the previous layer. So now suppose this size, instead of 512 cross 512, this size reduced down. So now you can say it is 480 cross 480. In that case, what happened? This size will also reduce, right? And because of this, these numbers will also reduce. And as these numbers reduce, your system will throw error because they always want the same number. Right. But in case of convolution operation, you are not worried. It will go to this part, then perform the convolution, then move to the next part, perform the convolution, and so on. So even their size is changing, they will not throw any kind of error, and it will produce with respect to the current size, whatever input is given. So that is your fully convolution neural network. Similarly, we have another network that is decon network, and that is based on the encoder decoder architecture. Right. So here you can say encoder part, and here you can say this is the decoder part. So what this encoder decoder is doing, it takes an image, it performs the convolution, max pooling, convolution, max pooling, and at the in between they here they have a bottleneck part, and this bottleneck you can say it generates some features here. Right. Now, in layman language, instead of saying features, you can say summary of this entire image. They have produces a summary. Now, what this decoder network will do, it will take this summary or features and then start doing the decoding these things. And you are using the unpooling here. Now, in case of unpooling, you produce again, unpool means max pooling means reducing the size, unpooling means increasing the size. So you can say from 7 cross 7, it will perform unpooling. Now it will become 14 cross 14. Then from 14 cross 14, it will again perform unpooling and it will become 28 cross 28 and so on. Finally, you will have the same size here and then you will get the output. That is the segmented output. Right. So now you can say how they have done the unpooling part. So in case of unpooling part, what they have done, they have taken this information and they have put it this information like they unpool it, and one is going here and rest will be filled by the pad, or you can say some zeros will be padded here, then two, then other zeros, then three other zeros, then four other zeros. So this information or this process is known as unpooling. Right. Now one challenge here, as we are not passing any pooling information, so then we are taking a standard unpooling. But suppose we got information of the pooling at which place it has performed the pooling. So for example, for this particular value, when it performed the pooling, so maybe the value will be 0 0.2, 0 0.3, 0 0.8 and 1. Right. So definitely once you perform the pooling for this, you will have 1 here. Right. Now what it is saying, another is it is saying, if you record the location of pooling, whenever you unpool, that will give improved result. If you are able to remember the location, that the unpooling will help you a lot, or that will give much better result. So that's why what we are doing, we are taking those locations also stored into the disk. While we decode it, then we will utilize those locations and then perform the unpooling. So what we are doing here, while we are doing the unpooling, you will have the location, right? And based on that location, you will give the value. So maybe that unpooling is taking, pooling is taken from this location, so you have taken this, then this location, this location, this location. So ultimately, the important point, if you are taking care of the location at the time of pooling, then it will be useful while we'll do the unpooling, and that will give much better result. Right. So here we have given, like while we are doing the pooling, you know this location. So we will use this pool map, and that is the switch variable. Switch variable is saying this is the location from where the pooling has been done, and these are the empty locations. So while we'll do the unpooling, we'll use this switch variable to perform the unpooling. So ultimately this switch variable is nothing, they are storing the location of pooling, right? And they will utilize while they perform the unpooling. Then second thing, we have seen the deconvolution architecture. So what deconvolution? Convolution means you are taking the bigger image and you have to perform the, like you'll apply the kernel over there and you'll have one output. Now deconvolution is reverse of that, right? So it will take one value and perform the deconvolution. So you can understand from this diagram. So here the input is this 4 cross 4 and it is padded here, and the output is this. So this is your deconvolution operation, or you can say one of the way to perform the deconvolution. So you can say this blue part, this is only the input, rest will be the padded item, means you have added it here, and then you perform the convolution and then it will produce this side. So input here is 2 cross 2 and output is 4 cross 4, right? So this is your deconvolution operation, because you need to expand the value, because you have make a bottleneck. After getting the bottleneck, you are expanding. So one way is to perform the unpooling, and second way you are using the deconvolution operation to get the higher values from the input. So in order to club them together, like that location part where we are using the locations and the deconvolution operation, a new architecture has been proposed that is known as the segment architecture. So what segment is doing, it is also similar as your deconvolute, but the change is they are storing the pooling indices, and that will pass on whenever they are performing the unpooling. Got it? So here additional part is the pooling indices that we are passing, and this is very popular architecture for the segmentation, right? So here you perform the convolution, here you have performed the pooling, and you store the pooling indexes, and that will reutilize while you are doing the unpooling in the similar place, or you can say similar dimension place. Similarly here, and so on. So this is the beauty behind the segment architecture. They are storing the pooling indices, right? Now, there is another architecture, that is the UNet architecture, which is very popular in case of your you can say segmentation, and heavily used in the medical domain, and dealing with the satellite data, dealing with any kind of segmentation process, or you can say many other applications. So what this unit is there, they are saying, so why unit is, because from where U is coming, its architecture style that look like something U. So that's why that name is given as a unit. Now what is the beauty here? What they're saying, they are saying while we are generating the output in the decoder place, or you can say this is your decoder part and this is your encoder part. So previously what we have said in the segment, we are just passing the pooling indices. Now they are saying if we pass only the pooling indices, might be that will not be that useful. What they are saying instead of pooling indices, we will pass the features itself. So what they are saying here, while they are generating the segmented output in the same level, they are passing the features here. So these features itself will pass here, right? And these features help them to build the segmented output. And that is giving very powerful results, or you can say very accurate results. Now you can say why this concept is useful. So suppose if you are able to recall, suppose I'm talking about the LXNet. In the LXNet architecture, in the initial layers, if you have checked the feature map, then they are belonging to the you can say very basic features like such as edges. So initial layer belong to the edges, belong to the color, belonging to other basic information like movement and all those. So while if we are storing these features and we are merging those features while we are generating the image in the same level, where they required edges, where they required the image, like you can say color and other things. So in that case, the output segmentation map will be generated. So the beauty here, we are taking the basic features or you can say features from the same location, same parallel location and passing while you are generating the outputs, right? So you can say these features belonging to the encoding part and these features belong to the decoding part. So means you have the basic features as well that is generated from the encoding part and you have the generated features as well. And this concept help us to make a bigger impact on the output. And that's why it is known as the UNet architecture. So I hope everyone have a basic understanding of the segmentation process, right? So first thing, segmentation is like pixel wise identification of the class or pixel wise classification. Then we have seen multiple architectures as well, right? We have seen like initially start with the deconvolution or deconnet or fully convolution network, then deconnet is there, then segnet is there, then UNet is there. If you check out more, then there is a res UNet as well, right? So these are very popular architectures for performing the segmentation task, right? Now next we will go for the lab. So and that lab is belong to the UNet, right? So let's jump to the lab. So please use this link and then we will go for the lab. So please copy or just take a note of this link so that we will just, so what you have to do, you just need to copy this link, go to the browser, a new tab, paste it. You'll get a Colab notebook. So just it required a browser and internet. That's it. So let me paste it here as well so that I do not have options to message.
Sir, chat box option is not available.
Yeah, that's right. Okay, so you just take a just give you okay. So this is the lab URL. Please utilize this URL so that it will be open at your end as well. Is there any ways I can communicate with the participants because it looks like all are muted.
Sir, I can share using WhatsApp.
Okay. Fine. So how they will ask questions? Suppose they have some doubt in
But
it.
last 10 minutes is reserved for question answer session. So using
Okay.
raise hands, they can ask the question. We can provide the mic.
Okay, great. Okay, so please note down this URL. I hope everyone has noted down this URL and then we can move forward. So just raise your hand once you have used this URL so that I can get an idea. Okay, you have used it and it is available at your browser.
So in between, they want to ask question, they can raise the hand.
It's just how I will be sure like they have taken this URL and opened in their browser. So participant, please raise. Okay. So many of you. So please raise your hand once you have used this URL and So I'm again opening this URL.
It is not opening, sir.
Just copy it and paste it. Means you cannot copy this. It's a tinyurl.com /lab -bu -unit. That's it.
It's not opening, sir.
What message is coming? I'm just opening this and so just use this URL. It's still not opening. Please confirm. Just make sure you are using tinyurl.com /lab -bu -unit. That's it. Nothing more is required.
Yes, sir. Got it opening, sir.
Great, great. Yeah. Okay, that's great. Yeah, thank you. So even you can note it down, and because the chat is not there, so just if someone can drop this into the WhatsApp group so that they can get it. Okay, so I hope everyone has opened this particular URL and you got this image, the very first image, that image segmentation using UNet, and here we have this image. So what we are going to do, we are making this architecture first. So we'll take some libraries, we'll take some data as well, and then we'll make this architecture, and then we'll train it and we'll check it. So let's move forward. So the very first thing what we have done, so here we have okay, just so in this part, what we are doing, we are taking the required library, right? So here we have NumPy library, Matplotlib library, PIL library to read the images. Then we are using the Keras library, and these like different con2d will be required, max pooling will be required, con2d transpose will be, concatenation will be required, Vaishnom and all those things, upsampling will be required. So these all things will be there, dropout, activation, and all those required functionality we have imported. Now you can see this first line. So maybe you have not seen this first line. So what this first line is doing, by default, if you use any Colab, they are using 2 point something version of TensorFlow, and there are many code or many you can say applications, they are still working on 1 point something. Might be you have made it like a few days back or like 1 year back, and you want to reutilize it, but intentionally you want to run the 1.7 version of the TensorFlow. So and you want to utilize the Colab. So if you use, suppose if you are not writing this line, then by default it will take 2 point something version, whatever latest in the Colab. But once you write this tag, so this is known as tag, then automatically your Colab understand, okay, now we don't want 2 point version or TensorFlow 2 version, I want 1.x version, means 1 point, it will take 1.7 or 1.6, whatever is available. So whenever you have intentionally required TensorFlow 1 point something, because in case of TensorFlow 2 and TensorFlow 1, lot of functions are changed. Their Keras functions are changed, their libraries are changed. So might be you have written your code few years back and you want to run it again here. So in that case, you require 1.7 version or 1.6 version. So just write this tag. So your system, or you can say Colab, will automatically understand, okay, whenever they will load the TensorFlow, they will load the older version, not the new version, right? So this is like a tagline here. Then we have used all the libraries, right? OpenCV and other. Right. Now let's move forward. Next, we have to download the data. So next we have downloaded the data here. Right. So we have downloaded this data. So we have taken this predefined data from this particular website, robots.ox.ac.co. So we have taken images, that is the original images, and their annotation. Now here the annotation is the pixel wise annotation. So if a particular that the class that we are looking forward, that will be annotated by white, and other part of the images will be annotated by the black, so that will overlap the things, right? Then we just done the tar like, oh, just expanding the things, and we have removed this bigger file from there. So just let me run it so that you can also run it at your end. Now we are getting some allocation quickly. Okay, so now we need to download the data. So quickly just download the data. I think we all aware, like just using the shift enter or control enter, you can run this. Otherwise, you can use this button as well to run this. Guys, if you have any doubt, just raise your hand in between. Yes, any doubt if you have. So someone raised their hand. Aswini and Kobri Priya. Yes, any doubt? Okay. How? Can you unmute this person?
Yes, Priya ma'am, you can unmute yourself and ask the queries if you have.
Okay, it's like great. So I hope you have downloaded the data. Now, once you have downloaded the data, next what we require, if you check out, we have to prepare the data, right? So in case of preparing the data, what thing we are doing? First of all, like, can anyone confirm, do we need to increase the size of text or it's visible or not?
Yes, sir, now it is fine.
Now?
Yes, sir.
Great. Okay, so here we want to generate the images, and what we have done, we have opened this annotation and the PNG file and mask. So this annotation is nothing, this is the mask. Mask, I can say mask is like, suppose we have an image of dog. So let's say or cat. It's easy to make the cat. So something like this. So what mask is there? So suppose this is the image, right? Uh, now this is your image, right? Now in case of mask, it will be look like. So this entire region, so you can say this region and like something like this will be only the white region, and so this region will be the white, and rest all region will be the black, so that once you put this mask on the top of it, you'll have only this region available, that will be the visible region. So this will be the mask. So this look like this. So this, whatever actually I colored, that is the white region, and rest of the region is the black region. Right. So this will be the white region and rest of the region will be the black region. So that this will be, once you will put the mask image on the top of this original image, only this part, or you can say only cat will be visible. So we have this mask and we want to create the images for that, right? So that this will become your annotated image. So then we have put it on the top of it and you got the value, the original value from the original image, right? So this particular code is doing the same task. They are taking the mask images and they are taking the original images and preparing the annotated data for us. So just run it. So this is more on the processing the data. So this is just a function. Whenever we require, we will call this function. Now next, we have just to open this file and this image generator will generate the image. So you can check out, we have made this function and now we have utilized this image generator to generate the train images and text images. Right? Here we have divided, sorry, here we have divided the files, the split file, and how you can define 95% will go for the training and 5% will go for the testing. So here we have divided the images. So now we have train and test data available with us. So once you run it, you will have train and test data available. Right? So just we have generated the images. So now if you run it, you can understand what I was talking about. So you can check out. This is the So this is your image. This is your mask. And this is your annotated image. Right. So what your system will do, or what your UNet will do, once you will give this input, the annotated output will be this. It will generate the mask, because once you put this mask on the top of the image, you will get this image. Right. So what it will do, it will generate this mask. What mask is saying, these points or these pixels are belonging to the dog, other locations are not belong to the dog. So you can say even it is masking this area as well, where because this is not belonging to the dog, this is some band or something is there. So that is put it over there. Now next, what we required, next thing that we required, how we evaluate it, right? So evaluation will done here. So we are taking this formulation into the code. So we are taking mean OUU. So here inputs are X, Y true, you can say the ground truth, and Y predicted, the original image, right? So you can say this is your ground truth, this is your predicted value, and based on that, it will produce the output. So IOU will be the return. So means it will give the quality, right? Now you can say why this IOU is really important for us. So if you are able to recall the training cycle, in the training cycle, the weights will update based on the error. Right? What error we are getting after the you can say forward propagation. Based on that, we perform the backward propagation and then we modify the weights. So ultimately, you should have some mechanism that will give you that error value. So this mean IOU will give you the error value, right? And that will tell you if you are good or not. So this will produce the error value for you. Okay. Now here we are making the model. Now you can say it is very simple to make the model. The very first thing what you are doing is just we are defining the function. So whenever you require a model, you just call this function, it automatically take it. One important point that I just want to mention, the input. Here we have fixed the input 256 cross 256, that we have fixed it, right? So that initial image whatever image will be the input, that is 256 cross 256, right? So whenever we are going to pass this image in this UNet architecture to process it to generate the segmented output, then you have to, you can say, resize the image into 256 cross 256. But suppose I don't want to resize the image. What I want my model should work on any variety of images. Just its size should be greater than a threshold. So suppose you are setting this threshold is 256. So if your current size is 512, then also it will work. If your size is 1020, then also it will work. If your size is 102048, then also it will work. Just it said more than 256, the thresholding size. Now you can say why thresholding is important. So if you go back, let me go to this UNet architecture. So on the top, if you go UNet architecture, you can check out here the size is reducing, right? So your size is reducing here, right? So what exactly it is doing? It is started with 572 cross 572, then it will become 284, and once you move forward, you can check out. Then it is 140, then it is 68, then 68, then 32. And then after 32 it again restarting. So means if your size is below threshold, for example, in this, for example, if you want to start, suppose I have taken the size, let's say I have taken the size here, just taking some size. So for example, you have taken 128 cross 128. Right. In that case, what happened once is go to the encoding path, and as it move forward, maybe once it will reach here, somewhere here, they have no pixels left. No pixels, because ultimately you are reducing. So maybe once you reduce somewhere here, you do not have anything to perform further operation because it's reduced down. As you perform the convolution, the size is reducing. So that's why you have to go more than threshold value. I hope it is clear why threshold, like more than threshold, is important. Right. So let's go back to the location where we was talking about this unit. So now suppose I want to perform like this. So instead of fixing the value, I want to give value, but just we have to make sure it is more than threshold. So what you will do, you will write here none. Now what none will do, it will accept any variety of input. You do not need to fix it, right? Once you pass none, then you can have any size of input. It can be 1024 as well, it can be 2048 as well, it can be 512 as well. Just it should be more than 256, so that at then suppose by chance you have given 48 cross 48 size image. In that case, maybe as it is moved forward somewhere here, the size will become 0 cross 0. Now once it becomes 0 cross 0, what you will do? You do not have anything to do. So you have to maintain that size. So that's why it should be higher than that threshold. So now once we fix the size, what next we are doing? Look at this point. Right. What we are doing. So here we are doing the down sampling. You can check out, we are doing the down sampling. This. What we are doing, we have architecture, so we require two convolution layer here, and then one max pool layer, and then again the size will increase. The you can say the kernel size will increase, and we will move forward, right? So automatically you can say we are creating such 6 layers. One layer, then second layer, then third layer, and fourth and fifth and sixth layer. Right. So whenever we do the you can say up sampling, then also we'll have 6 layers. Right. So now in the next part, that is now I think let me show the image so that you'll better understand. So you can check out here in the first part you are doing the convolution, two convolution, and then here you are doing the max pooling. So you can say this part, okay, let me go a little bit up. Yeah. So if you check out here we have con, then another con, right? And then this part is the max pooling. And that is required every time. You can check out that is required every time. Just your size is reducing down. Your kernel size is increasing and your size is reducing down. So you can check out like here we have given again con and max pool, con and max pool. So the same thing we are doing here. So let's do it. Okay. Yeah, here. So we have created that and done. Right. Then next is the bottleneck part. Now if you move, I think it is clear till now how we have creating this downsampling part. So here we have taken the loop means that will repeat 6 times because the structure will same, just your you can say your funds your uh, kernel size is increasing, so that we are increasing here. So ultimately once you run this loop 6 times, first time the kernel size will be your whatever the initial, that is f, so 8 you can say 8 depth will be there, then 16 depth will be there, then 32 depth will be there, and so on. So as it will be increasing, so depth will be increasing, right? So we have created this kernel size is 3 cross 3 and the padding is same, means while we are doing the convolution, that will not reduce the value or reduce the output size. Only max pooling is reducing the size. Convolution is not reducing the size, right? And then we will append this both the axes here, and after that we have performed the max pooling, and then again next layer, the next layer, the next layer, and so on, right? After that what we are doing, then we are making the bottleneck, means the bottom part. If you say u, so here the bottom part. Now in this bottom part you can check out what we are doing in the bottom part. Here we are taking the again two convolutions, then transpose, con 2D transpose. Transpose, you can say it's a kind of convolution operation, but reverse convolution. That is doing the upside of that, right? So in that you can say how you are doing the upsampling. So that upsampling is done by the con 2D transpose. Right? So how exactly this transpose is working? Something like that. Suppose you have this data. Let's say you have this data, like four values are there. Now what you will do, you will perform a convolution operation on this, but these four values will convert it into much bigger values, something like this. And maybe these four is belonging to somewhere here, or one value belong to here, one belong to here, one here, sorry, one here and one here, and then you perform the convolution operation. So automatically from 4 cross 4, what you will get, you maybe get 8 cross 8. So it is depend upon what kind of you can say transpose we are performing. So actually they are increasing the size. That will help you to up pooling the operation, the transpose operation. That is one way to do it. So here we are using the transpose, con 2D transpose, right? Now what we are doing, so here one time we already done this transpose. This is your bottleneck part, and one time we are doing the transpose. Now how many remains to upsample the things? That is 5 more times. So the same thing as we are going to repeat, we are doing here 5 more times, right? So 5 more times we are doing con and con 2D transpose. Transpose is like, again I'm telling, transpose is like up pooling. It is not up pooling, but it is behaving like a up pooling. It is increasing the size. First time we are doing the max pooling to decrease the size, and then con to the transpose to increase the size. And finally, once we have, so first is the downsampling, bottleneck, now upsampling. Once you club them together, then we will have the entire architecture. Now, one important part that is very important. What is that? Let me highlight it here. As we have checked out, as we said, it is concatenating the features from the previous layer. So you can check out here in axis 3, it is concatenating these two. X is coming from here, but previous layers at the same moment, suppose you are talking about this, suppose you are talking about this operation and this operation. So the features from here that will be concatenated here. So this features is layer J values, and that will be concatenated with the X. So with that way, you are doing the concatenation of the features from the previous layers and attaching into the next layer in the same level. So you can say here, if you are making this, so this will be attached here. This layer will attach features here. This layer features attached will be here, and this layer features attached will be here. Means in the same layer, we are attaching the features. So that is done here. And the same part, you can check out, that is done in this part here, right? So with this, you are able to make a complete unit architecture. Now you have a complete unit architecture, right? So once you're done with this, what next? At the end, you are doing the classification. What this classification is doing, you can check out. If that is belonging to the class that we are looking forward, then it will give 1. And if it is not belonging to that class, it will give 0. So means you have two class classification. And we already know whenever we talk about the binary classification, then the best function is the sigmoid. So you can check out, we are using the sigmoid function to perform the classification. Got it? So with that, we have done the classification task. So finally, what will be the output? For each pixel, it will say it is belong to 0 class or it is belong to 1 class. So in that way, you are doing the entire segmentation. Got it? So now let me run this so that your unit architecture will be ready. I have to run first IOU, shift it, and your unit model. Okay, so let me take 1 minute pause or 2 minute pause and taking the questions, because that is the most important part in this lab. Yes.
Good afternoon, sir.
Afternoon.
Sir, here in the program, we mentioned the threshold value, no? We are setting up with the 256 into 256.
Yes, yes.
Yes. But when
Right
you are
now
doing...
it's a 256 cross 256.
Yes, sir,
Very right.
256 cross 256. But when you
Yeah.
are using the UNet, we are going to decrease the size now.
Yes.
After the reducing the size less than the 256, whether it will be works on that or it will stops over there itself.
So if your size is going beyond, you can say 0 or a specific limit, then it will stop immediately. It will
But
say
actually,
no
in the
features found.
yes, in the above example, can you move for upwards?
Yes, of course.
It's image.
Yeah.
It's introductory. First starting sir. Unit architecture.
Okay, let me go here.
Yeah, here. In the case of unit architecture, here after 284 in the next layer we have the 140, no?
Yes.
That means after 284, because 284 is greater than 256, it will work, sir. After that it won't work.
No, nothing like that. This is the initial value from where your image size will start.
Yes, sir.
So in
Only for
this,
the input purpose we are
yes,
mentioning.
yes,
Okay.
yes. In the input size, for example, here it is mentioning 250. This is input size is 572 cross 572.
Yes, sir.
And in our code, we are taking 256 cross 256, right? So the
Yes.
idea behind that, your image should not be below than 256. Otherwise, what will happen once it move forward, maybe in the next layer, like next input layer, it will become 128 cross 128.
Yes,
Then
sir.
again, it will move, it will become 64
64
cross
and
64. Then again, it will 32 cross 32, right? And again, maybe it will become 16 cross 16, right? And at the end, it will become 8 cross 8 after 6 iterations. So 1, 2, 3, 4, 5,
Yes.
6. Now, suppose instead of 256 image, by chance, if you have taken 64 cross 64, right? So then what happened? It will first going to the 32 cross 32. Then second, it will go 16 cross 16. Then third, it will go 8 cross 8. It will go 4 cross 4. And then 2 cross 2. So
Yeah.
while it is reaching 2 cross 2 means you have only 4 values
Yes, sir.
from this 256. So you have summarized so much, maybe it will not able to generate the appropriate output
Okay.
because you have compressed it into 4 values only. The entire information that is belonging to 256 cross 256 images, that is compressed into 4 cross 4. And maybe suppose you have, instead of starting from 64 or 64, you have start from 32 cross 32. And what will happen after this? It will become 1 cross 1. So means you have only one single value. So then it will throw error.
Okay,
Right?
sir.
Error because it do not have anything to perform further up sampling.
Okay.
So that's why that minimum requirement is there. So that at least it should reach by maximum lowest 8 by 8. So that you will have at least 64 values that will help you to again reproduce the, well, you can say segmented output.
Okay, sir. Thank you, sir.
Great. Okay, great. And any other quick question, please? Because this is really important to understand. Yes, any other quick question?
Sir, how to choose a mask? Which type of mask we need to use?
Okay, that is depend upon your problem. Means this is not a specific like what type of mask we have to choose. It's a depend upon your problem statement itself. Someone has raised a Silpi. Could you please give permission to unmute? Dr. Aswini also. Yeah, Silpi. Silpi Agrawal, could you unmute and just ask your question, please? Okay, Dr. Aswini, you have.
Dr. Ashwin,
Yes, Silpi. Please go ahead. What's your doubt? Dr. Aswini, I think you have asked some. Yes, please. So please unmute and speak up. Both have doubt. Please unmute. Yes. No, first unmute yourself. We cannot unmute.
Ashwin sir, unmute yourself.
Just unmute from your side. Now you have permission. You just unmute your side.
Sir, you have a permission.
Yeah. Silpi also not able to unmute. It looks like they have permission but unable to unmute. Okay. How I can interpret? I don't know.
Sir, you have the mic. You can unmute yourself and you can ask the query if you have.
I think his mic is not working most of.
Okay. Sir, you can post your query on the WhatsApp group. We can ask on your behalf.
Okay. Silpi Agrawal, you just try if you can unmute and
Yes, Shilpi ma'am, you have the mic. Please unmute yourself. Shilpi ma'am.
okay. Mm. So now I think
Sir, actually,
Satish,
sir ने question भेजा है.
yes,
So sir
please.
was trying to ask that how can we select mask region?
Okay. So the selection of mask region is the manual process. The manual process means you have to utilize some tool to do the annotation. So for example, you are using label me. So in the label me, so for example, I think one session is also there to annotate the data. So let me give you a brief of that, how exactly it will work. So for example, you have an image, right? And that will be load into the label me tool. Now you will get a mouse pointer and suppose you have a person here and you have to annotate this. So what you will do, so for example, you want to do annotation for object detection. So you will have a box like you can say a line like you are doing in the paint. In the paint, you are selecting some region from the image. In the similar way, you are doing in the label me. You are selecting some region. And once you select this, what label me doing, it will generate a JSON file. Right, what JSON file contain, it will contain the coordinates of this region. Right, similarly this is for object detection. Might be if you are doing some like segmentation task, so what they are doing, they have, so you have to do multi-point, you can say selection, like most probably you have done in the Word or somewhere. And then once you have this multi-point selection in this way, and once you've done it, automatically this all points will be recorded into the JSON file. So means creating the mask is a manual process. A person need to sit around and use the tools for the annotation, and then only mask will be created. It is like nothing like any program is there that will create the mask, because that we are trying to do, to generate the mask automatically with the help of UNet. So this data creation process is the manual process for getting good accuracy. Semi-manual is there. Semi-manual is like suppose you have some code that will do some annotation, but later on manually you have to check for better accuracy. Otherwise your accuracy cannot go beyond that tool. Ultimately you are relying on that tool. So that's the way how you can do the annotation, and you are getting the mask. Yeah, Silpi ma'am. Sure.
Yeah, thank you, sir. Now my mic is
Oh,
on.
great.
Actually, there was no permission, but now it is activated. Yeah.
Great.
Actually, sir, my question was again that is, suppose in a dog image, if we only want to identify the eyes only, for example,
Mhm.
like, or in a specific region of a particular image.
Right.
So for that, we have to first create a mask.
Yes, you have to manually create that mask. Once your model is trained based on, so that is like creating the training data. So once you've done that training data creation, then you train a model, and after that you do not need to do it manually. Then your model
Yes.
will do that task for you.
Any tools for that, sir?
Yes, there is, as I told you, label me is one of the tool that will help us to creation those annotation.
Label mean.
Me. LABELME.
Okay, sir. Thank you. Thank you very much, sir.
Yeah. Welcome. Yes, one more person have some query. Yes, Dr. Ashwini, please go ahead.
No, it's okay, sir.
Okay, fine. Okay, so let's move forward. So now we have created our UNet architecture. So we can see like we have three parts. First part is the downsampling part. Second part is the bottleneck part, and third is the upsampling part. After that, we have done the classification. Now with this, just we are calling this function to create the model. So this is just creating the model. Now, if you want to check the summary, you can use this code to check the summary. So you can say with that code, we have generated this much big model. So you can check out input layer is there. So again, it's a 256 cross 256. Once you want to make it free from size, then you will put none here. So let me do it. It will none separator. And then you have created a UNet architecture. And then once you check the summary, the beauty here now it is do not have any predefined size that it should be only 256. Now it will work T56 also, it will work 512 also, it will work 1024 also. Right. So many times it happens. Suppose your image size is very big, like size is 20,000 cross 20,000 pixels. So might be once you load this image, it itself is like a 3 GB image or 4 GB image. So maybe you are not able to train your model. So what you can do, you can reduce first size of the image. Let's say I have make that 10,000 cross 10,000 images into 1024 cross 1024. Right? Then what you'll do, you have trained the entire model after converting it. Then what you can do, then if you put it the none cross none, then it will work for any size bigger than that. Right. So then you will give 10,000 cross 10,000 images for the testing and you are producing the appropriate output. So that is the beauty behind giving this none. You can go more than that. Yes, definitely. If you go below than that, after some point, it will start throwing the error while it will not have enough size. So let me take it back to 56 cross 256. And then I'm creating the here we have model summary. Now I'm taking back, so that's why it is giving. So you can say check out the output is 256 cross 256 cross 1. Why it is 1? Because it is producing one-dimensional output. A two-dimensional output, but depth is 1 only. It's because the values are either 0 or 1. That is the output from your segmented, or you can say mask region. So it will produce the mask for us. Now here we have callback function. This function is really important. Why it is important? What this callback is doing, after every epoch, if you want to perform some operation, then you can make that as a callback function. So after every epoch, this callback function will, you can say, activate it. What it will do, so it is useful for saving your temporary model. For example, you have written in the callback function like if your model has better accuracy, then only you will save it. Otherwise, you don't need to save. So every epoch, if you are improving the accuracy, your new model will be updated, right? And maybe suppose your because of power failure or because of any reason, your process is turned off, then also you are not empty hand. You have your latest model which have gained some accuracy itself, right? So that is the beauty behind callback function. Along with that, if you know like is your model is overfitting or not, so then every epoch you are checking the test state dataset accuracy and train dataset accuracy. And as you know, if your test dataset accuracy is dropping down, but train dataset accuracy is increasing up and up, then you can say, okay, it's a condition of, you can say, overfitting. So you have to stop the process. So that's these all things you can put into the callback, and based on that, you can identify the results and identify many other things. Now, suppose you want to plot after, like in the research paper, you want to plot the function for the losses, you want to plot the function for the accuracy in every epoch. What is the graph for accuracy? What is the graph for function? So these all things you can store with that callback function, and it will start the plotting the things. So that is really important. So let's make it for you. So what we are doing here, we are just model checkpoints. So we are creating the checkpoints unit.h5 every time, and we are making this plotting function as well. So we are storing it on every epoch. At the end, what we are doing, we can plot it. Right? So that's the way how we can make the this callback function. Now here it's a training part. So just simple fit generator to train the generator. So it will train it, and here we have given only 2 epochs because it is taking a lot of time. So every epoch it will give some output. Right. So here you can say while we are training, we have used this callback function. So every epoch this callback function will be called, and you will get the output based on that. Validation data, every epoch it will check is your accuracy is going down in the validation data or going up, to check out your model is overfit or not. Right. So these all things we can make in this generator function. I hope everyone in the same pace, and if you have any doubt, because it will take few minutes, so if you have any doubt, then we can utilize it for the discussion. Anyone, any doubt? You can raise your hand if you have any doubt. Then let's wait till it is training. It will take 2-3 minutes. I hope everyone is able to train this model. Now later on you can modify as per your desire, as per your application as well. And you can start with this as a base thing. Then you just modify the training data and testing data. You can increase the depth of the unit architecture. So right now it's 6, so you can increase or decrease as per your desired uh, output or desired application. So if it is very complex, you are looking for very minute values, then you can increase the depth, and if it is more shallow, so then you can decrease the depth as well. So after one epoch, I got this image, and this is the you can say the mask that is generated by your unit architecture. And after putting the mask on the top of the image, I got this image. So definitely you will not get very high quality result in 2 epochs. So you have to run for longer epochs to get a very good result. So just you change the number, and before going to sleep, you just increase this number like 20 or 30, and then once you wake up, your model will be trained. The only problem with this collab, it will not run more than 12 hours. So you have to save your things before 12 hours, otherwise it will refresh and everything will be gone. So you can say in the first epoch, it has very blurry, you can say output, but in the second epoch is much clear. Definitely it's not perfect, but much clear. So if you run it for more epochs, you will have much better idea. Right. Now I want to do a prediction with a new image. So let's take this. So I'm taking one image downloaded and have done predictions. So it's a test image. Let me check. Is really it is the test image? Yeah, I just renamed it as a test image. So whatever we are doing. So we have to create, open the image, resize it to 256 cross 256. Here we have done the normalization, and then we are passing this into the our model, and model will produce the output, and based on that it will take. So let's see. So this is the output from, so this is the image that we passed into the model. This is the mask that is generated by your UNet architecture, and this is the generated image once you club the mask and the image. Right. So I hope like you are able to understand this entire process to get the input, get this like how to create the model, and how to like input the data here. Then similarly you can check out like how to generate the images from the mask, from the annotation, and after that you will see like you will split it. Now one important point here, we have split in the simple way, like very simple way. You have split it, like you have taken first few numbers for the training and later few numbers of the testing, right? So this can have one problem, like suppose your data is stored in alphabetical order, then that can be a challenge. Maybe in the later part, that kind of data your model never seen during the training. So first you have to randomize the data, and then you have to do the splitting, or you can use the predefined functions for splitting data into the training and testing. That is in the sklearn. So this like just a visualization. There is IOU matrix that is checking the you can say the quality of result, right? Intersection over union. Then we have generated the model, three parts, majorly three parts: down sampling, bottleneck, and up sampling part. Then finally we have done the classification, where we have the output in 0 and 1 form, right? Here we are using the optimizer RMS prop, then binary cross entropy, and so on. Then we just check the summary, and here we have done some callback to store the things after every epoch, and finally we will train it and checking it that with the new image. So this is all about the UNet implementation for image segmentation. So now it's like next like a few minutes for the question answer session. So please ask if you have any doubt. No, someone has some doubt. Devi Das, could please enable Devi Das to ask the doubt. Yes. Can anyone please enable Devi Das to ask the doubt?
Hello.
Ashish sir, Madhu ma'am. Yes, please go ahead.
Sir, I am audible. Yeah.
Yes.
Sir, I have a doubt that during training, is it always or is there any strict criteria to choose the validation set, or we have to choose it randomly? Because sometimes what happens, because of validation set, accuracy might not be increasing as per our requirement. Sometimes accuracy may get means it will bring with the training accuracy. So is it true, or we have any other idea to select the validation set?
Okay, so suppose you have a large amount of data, so that belong to two different things. Suppose you have large amount of data, so from there you will randomly pick some part of the data, Now, whenever you are randomly pick some part of the data that you can say validation data, you have to check the distribution. Distribution means suppose you have 10 classes. So in the validation data also, it should like at least few data belong to all the classes. Means it should not happen. It has only 3 class of the data in the validation set and the rest of the data doesn't have in the validation set. So the distribution should be good in the validation data so that it can check properly like is really our model performing good in all type of classes. That is one part. Now second part, suppose we do not have enough amount of data, right? We have a very limited set of data. Then you can utilize the cross validation concept. So in the cross validation, what happened? It will check the like suppose you have 1000 data points, let's say, and you are putting the cross validation is 10. So what it will do? It will divide all these 1000 data points into 10 parts. So you can say 100 data points in each part. Now, out of these 10 parts, it will pick one of them as a validation and rest of them for the training. When the next training iteration, it will take another one for the validation and rest 9 will be the training. So in that way also you can make the validation set and that will be a really nice training as well and it will give good results as well in terms of validation.
In case of large size of data, is cross validation the good choice or checking distribution and selecting samples from each class?
Cross validation is time consuming process. If you want to go with that,
Validation is
that's fine.
the good way.
So like suppose you have 1 million samples, then you do not need a cross validation kind of things because unnecessary it will take a lot of time to train.
Because validation may take a lot of time, cross validation.
Yes, definitely.
Thank you, sir.
Welcome. Yes, a good question. Yes, anyone, any quick question?
Sir, one question is available on WhatsApp group. How can
Yeah,
we
please.
annotate if multiple objects in single image, and how can we annotate occulted object?
Occluded object.
Occluded. Yes, sir. Occluded.
Okay. So if you have multiple objects, then also you can annotate because it's not like only one object you can annotate in one image. So you can annotate multiple objects in the same image and it has separate labels over there while you are dealing with this label me tool, right? Now, occluded object, you cannot annotate the objects which is not visible, right? Otherwise, the algorithm will understand, okay, if you have like, for example, as a human being might be, we can say half of the body is behind the chair or behind the car or something, right? But whenever you will do the annotation, you will only annotate the region where it is visible. Otherwise, while you will train, suppose you have annotated the entire image to just make us understand like as a human being, like leg and other part will be behind the chair. So once it is trained, what it will say, it will understand chair is also human. So then automatically it will start showing chair as human because your annotation is saying that. Right. So make sure whenever occlusion is there, you have to annotate only the visible part, not the background part. I hope it answered. And you can use label me tool for that, the annotation. Yes.
Sir, one more question is there on the WhatsApp group.
Yes,
that
yes.
can we apply our own kernel as pre-processing?
Yes, of course, we can apply our own kernel as a pre-processing if we have some image processing. So definitely we can apply, and that features that is coming from that kernel, that will become input for your model. Definitely we can apply. But whenever we test the model as a pre-processing, we have to apply those kernels into the testing image as well while you are testing the image. That's the only thing. Yes, definitely we can use it.
Hello,
So
sir.
yes, yes.
Sir, one more question is there.
Yes, please.
Sir, in case of UNet, if we have multi-class segmentation, so in that case, in the output layer, let's say output layer of the decoder, where we can receive the segmentation map. So in that case, what should be the right choice for activation function, whether we have to use sigmoid or softmax for multi-class segmentation, so that we can
Definitely,
get good
it
results?
cannot be sigmoid. If it is more than two classes, then it cannot be sigmoid. It will become softmax, so that we can handle multi-class classification. Because at that time, it's a multi-class classification. Definitely, even it's a one pixel, but it's a multi-class classification. So you will go with the softmax as a output.
Thank you.
Yeah. Yes. Any other questions?
Yes, dear participants, if you have any query, you can ask. You can raise your hand, we will provide you the mic. Sir, I think no more queries are there.
Oh, that's great. And even if you have any query, you have next 1 hour, because after 1 hour we again meet. So you can ask at that time as well. Okay, that's great. So thank you everyone for joining this session, and thank you to giving me this opportunity to discuss this particular uh, technical ideas of segmentations and their implementation.
Yes, thank you very much, sir. Thank you very much for your wonderful hands-on session. And this hands-on session always increases the confidence to use the technology. And I hope participants have learned and practiced hands-on along with the session. And this will definitely help them in their future work and the research work. Thank you very much, sir.